to my talk. There's another subtitle to my talk, which is really the role of noise in such processes. And in particular, there's really rich physics in trying to understand this noise and in fact using it as a resource in particularly noisy quantum systems. So that's really the nutshell summary of the talk. Let me start by showing you this image. This is a image of one of our multi-qubit processors that we fabricate at Berkeley. And just to give you a sense of the technologies involved here, the qubits are made from Josephson junctions, and hopefully you'll be able to see my little mouse pointer here. Those are the smallest features here, which you cannot see. The gap here is of order, between tens and hundreds of microns that are there. These junctions, which are submicron, are then connected by wires that go ahead and form the resonators. And in fact, then individual qubits are linked by other wiring channels. So it's quite amazing that the community now is at the level where we can put together many such qubits. On one hand, that gives you the resource to produce complex entanglement, that is a resource for computing. But one of the major roadblocks in superconducting technologies is that we have lots of error processes in the system, lots of noise. And this noise causes decoherence, infidelity in gates, and so on and so forth, and limits the type of quantum computation you can execute. But what I want to talk about today is that noise itself is actually a very interesting problem. And in fact, many of the techniques of quantum information science and information theory can be applied to them. So with this picture, I wanted to temper expectations by sharing with you this very famous quote of Rolf Landauer. I think his other quote, "Information and physical," is more famous. But if you read his obituary that was written by Seth Lloyd at his passing, this is one of the quotes that's there. And it says, "This proposal, like all proposals for quantum computation, relies on speculative technology, does not in its current form take into account all possible sources of noise, unreliability, and manufacturing error, and probably will not work." So I think he was spot on for many of these things, and I thought that's a good way to start this talk. So let me share with you this nice image in the upper left, which I've surreptitiously taken here, but I've credited here to the Innsbruck group because it's really beautiful. And it shows the idea that if you have, let's say, a quantum system, a quantum state shown here by psi, and in fact, you have many controllable degrees of freedom, in this particular case, trapped ion qubits, then one imagines having a large extended array of such qubits. And this turns out then to be an engineered quantum complexity. We are looking at this exponential complexity that we are controlling fully, and that becomes then a natural resource for quantum computation. Predicated on that idea is that you have full quantum control of the system. We're able to manipulate all of these qubits and also produce entanglement between them. We also have minimized any unwanted entanglement to degrees of freedom in the environment, and such things would cause decoherence, for example. So quantum circuits, and what I mean here is not the superconducting circuit, but quantum circuit in the sense of a gate sequence, would actually be then used to perform a computation. So then what I would like to show and point out here is, let's imagine that we have the case where we don't actually have such full control. We have really an open quantum system. And what I've done here is I've grayed out all those other qubits because I'm unable to control those. And let's imagine I just have a few qubits in the center that I can control. Then few qubits in a noisy environment. This is in fact random quantum complexity. The linkages are still there in this many-body system, but I don't control all of them. And this indeed then becomes a test bed for many-body quantum physics. So now I have partial quantum control of the system, and I have random interactions with the environment. And what I want to point out here is quantum circuits, gate sequences, again, are particularly useful to probe noise dynamics in such a system. And just taking a little bit of a physics perspective, I think it's quite interesting that and powerful that these methods of information theory based on quantum gates and gate sequences, etc., are really complementary to the things that we have learned in AOMO physics and condensed matter physics. So in such traditional fields, we measure noise by looking at spectral densities, by looking at correlation functions, so on and so forth. And these are very analog quantities that you use to study noise in a system. In this case, the system is digitized, but the formalism of quantum circuits is extremely powerful. You can go ahead and measure very rapidly any type of correlation function in your system, whereas in a traditional condensed matter experiment, it's not so easy to do so. So I hope that also garners some interest from the basic physics community of why we're looking at these things. Okay, so before I go on to the particular material in the talk, I do want to thank my group, and they're assembled here outside the clock tower in Berkeley. So let's start talking a little bit about errors and how to parameterize them and the like. So I'm going to just represent it for a two-state formalism, the block sphere shown here with block coordinates x, y, and z. And in particular, let's look at a pure state on the surface of the block sphere shown by this black vector, and there's a dot at the top of the black vector. So I can imagine a noise process where I lose the purity, so to speak, of this state. So in fact, the block vector will shrink from its position shown here in black to one in red. So this type of noise process I can describe by noise channel, shown by this curly E here. And this noise channel is operating on some density matrix, rho here, and it has a probability of occurring little p. So what's happening here is I take the density matrix, and in fact, I am shrinking its length equally along the x, y, and z directions shown here. And this is how one would write that particular type of noise channel. And you can just check the mathematics here. If p is 0, meaning you have no probability of error, you just have rho, the density matrix, coming back to you. We can then think about the complementary piece here, saying that if I now parameterize my state in terms of Pauli operators, so I can use 4 operators to describe the identity plus the 3 Cartesian directions. So this matrix capital lambda will act on this type of parameterization of the density operator here. And again, the identity part here is left the same, but in fact, I have a shrinkage along the x, y, and z directions. Okay, so this represents a purely depolarizing channel where I've gone ahead and just simply reduced the length of the block vector. And we can write such matrices for all the different types of noises that we think occur in the system. A dephasing process, for example, would be a rotation, let's say in the xy plane here. And in fact, I put this probability of error only in the x and y components, say, of this Pauli transfer matrix. Okay. Now, I want to distinguish this type of error where I'm losing the purity of my quantum state with another error where, in fact, the length of the block vector is unchanged. But in fact, what is happening is that it's being rotated unnecessarily or unwantedly on the surface of the block sphere. So this is a coherent error. So in this particular case, I want to hit some target state shown by, let's say, this gray arrow here. But in fact, I end up somewhere in this blue zone. One exemplar of that is the arrow shown, and I'm off by some angle epsilon, say, or some small error epsilon. So this error matrix basically looks like a change of basis or a rotation in quantum mechanics. And you can write that here in terms of a generalized rotation matrix, cosine minus sine, sine, cosine. So to give you a sense of the physicality of these errors, this type of pure depolarizing noise would be decoherence processes where information is lost irrevocably to the environment. And the purity of your state goes from something that's unity to something smaller, to a mixed state, say. And coherent errors could be imperfect rotations from your control electronics. Although those are in pretty good shape these days, the real problem quite often is crosstalk, right? You have 2 qubits that have unwanted coupling quantum mechanically, and you drive one, but in fact, you end up rotating the other one also. So these are 2 basic types of errors. And one question that you may ask is, well, what is the dominant error? And then how do you actually benchmark these errors? And how do they actually affect the performance of a quantum computation? So the first point I want to share with you is that having these types of stochastic or depolarizing errors, random errors, is actually very, very different than having coherent errors. So let's do just a little bit of math along the way here. So if I imagine now having this type of error channel, I wrote down the error process for you last time on the last slide. If I now do this n times, let's say I have n errors, then how do they accumulate? And you can see that I can imagine this infidelity going as 1 minus p. So the overall fidelity drops from unity times 1 minus p to the power n, right? So I have n iterations of this error process. And if p is a small number, you can go ahead and Taylor expand this 1 minus p to the end, and you simply end up with n times p. So this is a linear accumulation of errors for this type of uncorrelated or stochastic noise. The situation for coherent errors is actually very complicated and very different. So let's imagine the following. I now have this type of error matrix. I can now try to think about how these errors accumulate. And let me just graphically with my hands and also my words tell you that you see you can have very different situations. Let's imagine you have this error applied 5 times. So you do one rotation. The other rotation, in fact, could bring you back, right? In fact, you can undo the error. Or the next rotations could actually just add up and take you very far away from your state. So you see, it's not obvious, actually, what happens after these errors. In the worst case, they will scale quadratically. That's to say that all of them are going in a direction which is just aligned and moving you away from your target state. So in this case, we can imagine applying this rotation n times. So you'll end up with the 0 state rotated through an angle n times epsilon, and the same for the sine piece here, n times epsilon. So if you Taylor expand this again, the cosine part now will go as 1 minus this n squared epsilon squared, and the sine part simply goes as n squared epsilon squared. So you see the accumulation of errors compared to the process on the left is quadratic rather than linear. So these are more pernicious than stochastic errors. Moreover, there's another very subtle piece that sometimes can be lost, which is what is the impact of this gate infidelity on some kind of quantum operation or quantum computation that you would run. So you can imagine taking this matrix shown here and applying it to your density operator. And if you do that, then you see the diagonal elements, they scale as cosine. And cosine, if you Taylor expand that, is 1 minus epsilon squared. So the leading order term is unity. The first correction that comes in is epsilon squared. The sine part actually is linear. The correction is epsilon. So if you measure a certain error rate along the diagonal, the error rate due to the off-diagonal elements is much worse. Okay, and that's actually very important because you could measure, for example, as I'll show you in the next slide, rather easily what are these diagonal components of this matrix. And let's imagine that you are at some 10 minus 4 threshold for an error correcting code. Actually, the error that you should worry about is the off-diagonal elements would be 10 to the minus 2, which is significantly worse. So let me go ahead and walk us through that and see how we can benchmark that and perhaps even mitigate that. Okay, so the first point to think about is as these quantum systems increase in the number of qubits that you have, the complexity of error processes also increases. So there are many things that can go wrong in your system. And the question is, what are different ways to characterize that? So again, you can think about here having a block vector that I want to actually characterize, shown here as the North Pole, right? So I'm just going to look at a target state, which is right on the North Pole here, where the 0 is. And I'm actually going to end up with a row which is away from that. Okay, so then you can ask the fundamental question, well, how do I check these two vectors, or how do I parameterize that these two vectors are different? So the simplest way you can do is just take the dot product of those two things, right? So you can see here, I've taken the dot product of rho with the 0 state here, and you get the fidelity here shown in blue, right? So this is basically a fidelity or overlap type of metric. So immediately you see that you've lost some information. You have some idea of how much of this vector is aligned along the North Pole, but you don't know anything about the angle. Right? You've given up that information in decimating some complex information into a single number, which is the fidelity. So this is typically what is done in randomized benchmarking. We go ahead and use a fidelity or overlap-based metric to get a very simple number at the expense, of course, of understanding what actually is happening in your error process. The alternate approach here could be, well, let's look at the vector difference, right? After all, the 0 state is a vector, rho is a vector. What's actually this difference shown here is this red arrow, and we can call that D, and that's in fact the trace, let's say, between the 0 operator and the density operator that you have. So these norm-based metrics, because now we're actually looking at a distance, and there's many of them. You can think about the trace distance or the diamond distance or the diamond norm or the total variational distance. You may have heard these terms. So all of these are measuring somehow this vector distance, which is there. And so the idea is that none of these are more fundamental or not than the other. They're just measuring something very different in your quantum system. So if we look at the first one, where we're looking at fidelity-based metrics, there we're basically measuring an average error rate. So you can say, I'm going to prepare this state rho in many different places on the block sphere, look at the fidelity, and then that gives me an average F, right? And then quantum mechanically, that's what's shown here. So I have some error channel curly E, and I put it between some, if you like the proper word, some Haar distribution of states that are there, and looking at what the average overlap is and getting an infidelity from that. So that gives you the average error rate. Now, the other thing that you can do is what about this vector distance? And as I mentioned before, depending on how these errors add up, this can be a big or small number. So we can define something which is the maximal error, and that's shown here by something called the diamond distance. This is the worst case error rate. And mathematically, it comes up pretty straightforwardly, telling you it's the supremum, what's the maximum distance that you can have for this parameter D. That's there. So these actually give you very different bounds, right? One is this linear bound that says my error rate is this R, and that's if I have a purely stochastic channel, But if I have something that's truly only coherent errors, then the right number is square root of that, right? Like the 10 minus 4 and 10 minus 2 I showed you on the last example. And this diamond distance, which is telling you this maximal error rate in your system, will actually go between the lower bound and the upper bound, depending on whether you have stochastic errors or coherent errors. So that's an interesting thing to measure. Do I really have stochastic errors dominating my system or coherent errors? Okay, so now let me actually show you some data and measurements going forward. So again, I've used this word randomized benchmarking. Let me go ahead and put that in physical terms as to what that process is. So let's imagine you start with a state psi, okay, and you apply a gate, let's say a 90-degree rotation, and so on and so forth. Let's imagine that rotation is not exactly 90, but you did 91 degrees or something else. So as you do more and more rotation, that error is going to accumulate. So the idea here is that you apply a certain sequence of gates, m of them, say, and in the last gate, you try to undo all of that. And if you undid that sequence, which you kept track of, you should end up with the unity operator. But you don't. You have some errors. And the longer you make the sequence, the more this error accumulates. And that's shown here as this exponential decay. And that's really the essence of vanilla randomized benchmarking. Okay, so we'll go ahead and use a random sequence of gates, say Clifford gates or Pauli gates or whatever rotations you want, and then try to undo them and see what the infidelity is. So what's actually happening here in this randomized benchmarking protocol, the physics underneath this, is something which was actually discussed by Bennett and Broussard many, many years ago. It's the physics of twirling. So the idea is as follows. Their original paper was entitled Purification of a Noisy Environment. So what's happening here is I take this matrix lambda, which I showed you before. That's an error matrix. What happens to that matrix if I sandwich it between rotations, say of the Clifford set or some other Pauli set, in this case, the Pauli set, what does that error matrix look like? So I've shown here in a very simple example. Let's imagine I look at a 10-degree rotation. Okay, so I'm going to have a misrotation of 10 degrees. The error matrix for that looks like this. In particular, I'm rotating along the x-axis, so I'm in this corner of this 4x4 matrix. So then you can see, well, what if I actually take this rotation now and sandwich it between two x rotations, two y rotations, or two z rotations? Okay. If your operator commutes with the original process, then in fact nothing happens. In other cases, you see signs are flipped, so on and so forth. So if I add then these permutations together, you see I've killed the off-diagonal components, right? So in fact, I've twirled away any of these off-diagonal components. And in fact, you see, this is what randomized benchmarking is doing. You're actually sandwiching between all these random rotations, and you're ending up moving the noise to the diagonal component, which you then measure. So the tricky part here is, yes, you have now a measure of the error rate, but you don't know what the error is, because in this case, as I showed you, the original error was a 10-degree misalignment here. So again, emphasizing the idea that you can decimate something complicated into a single number, but one must remember that you're losing some information. So which type of error do we have? So there are multiple ways to measure this. So we can do our standard randomized benchmarking, okay, and we measure what's called the overall error rate, right? That's the total error. And in this case, it's 10 minus 3, say, for 4 of these qubits shown here in a multi-qubit processor. You can measure this for single qubit gates and 2-qubit gates, right? The errors are here, much worse, of course, in the 2-qubit case. And then what you can do is a modified process, which is called purity benchmarking. So you do the same thing as randomized benchmarking, but at the end of the sequence, you measure the length of the vector by tomography. So that gives you the rate of coherent errors. And as you can see on both of these things, we're actually dominated by coherent error, not the stochastic error that's there. And what you can do is actually do a type of tomography to really measure it, at least at the level of 2 qubits, what all these errors are doing. And there is a process called gate set tomography. So tomography in the usual quantum sense means you measure all directions of the vector. You can translate that into a more speedy ways where you're using different circuit sequences to measure that. And now this is what the true error matrix looks like for a 2-qubit gate that I'm running. So this is a controlled Z gate, and you can see there's errors all over the place. So you can see all of these coherent errors that are there. So the idea then is, well, what if I actually use this twirling idea and integrate that into my gate sequence, right? I'm using twirling for benchmarking, but maybe I can use it for computation also. So the way to implement that is, if you think about, again, trying to hit this target vector here, every time I do this, shown in orange, I miss by a different angle. So if I take the average of those, then I've actually shrunk the block vector. So this is the key piece. You can take these coherent errors, but in fact, by adding randomization, you can turn them effectively into stochastic error. Okay. And this is real data showing you that this, in fact, is working quite nicely in our system, where, again, the orange dots represent the different instances of this coherent error, which on average shrinks the vector. Okay, that's there. How does that translate actually into a circuit? So let's say this is a quantum circuit that I want to execute. Okay, so it has a certain set of gates here, X gates, T gates, so on and so forth. So C naught gates here. Then what I actually go ahead and do is I insert these random gates, but I insert them in a way that I undo their effect right afterwards. Okay, so at the end of the day, then in fact, I end up logically with the same circuit. So here I do a Y rotation, I do another Y rotation after that, so on and so forth. So then I can actually compile these and just have different angles. So in fact, I don't have any additional operations that are there. So if I start doing this randomization in my CZ gate, you can see what error matrices I have ending up after I do, let's say, no randomizations, one randomization up to 100. And you can see even after just 100 instances of adding these random gates, my noise model is now looking significantly more like a simple depolarizing model. So I've tailored the noise from this coherent noise into this stochastic noise model. Okay. And again, I can actually go ahead and characterize the fraction of my total error in the same way that I showed you before as a function of the number of randomizations. For a CZ gate, I start off with having more coherent error shown in blue than stochastic error shown in this orange type of color here. And as I increase the number of randomizations, I get to the limit where, in fact, I'm dominated by this. And in fact, I don't have to do this for one 2-qubit gate. I can look at the set of all 2-qubit processes. And you can see overall, for all of them, there is, in fact, improvement in this way, or at least tailoring in this way. Okay. So what about this vector-based metrics? How do we compare this? How do we capture that information, showing us the difference between the stochastic errors and the coherent errors? So what I've shown here is the error rate, okay, as a function of the number of randomizations. The axis will come in a moment. So what you see here is this line shown in so gray here. This is basically this randomized or benchmarking, or in this case, cycle benchmarking error rate. This is where I'm measuring the diagonal. Okay, so this is the lowest error that I have. Then if I actually go ahead and I measure using this tomographic method, I can also measure the diagonal of that matrix. After all, I showed you the full matrix. If I measure its diagonal, it gives me this process and infidelity, just like randomized benchmarking. And that's shown in blue. So that agrees well here. The vector-based distance, which I can calculate, it's the one norm. So I calculate the diamond distance, and you can see it's much larger, okay, in this case for no randomizations. But as I start to randomize the system, then I actually saturate the bound. And this is actually quite nice, right? And I can do this for any 2-qubit gate as well. So I actually go ahead and improve the maximal error rate. And in fact, if you look at this dashed line here, this would be, let's say, what you call out as a threshold for the surface code, say. So I've used here 10 minus 2 here for the error rate. And you can see here that in the case of no randomizations, the total or maximal error rate is well above this threshold. So on average, your error rate is low, but in fact, you do have a very large coherent errors that are there, which are not shown in the average. But I actually cross this threshold as I go ahead and randomize things. So in fact, what I want to mention here is that the physics of it is that the diamond norm converges to the average error rate, but I would say more specifically for quantum computing, that you're now truly crossing the threshold for fault-tolerant operations if you randomize them. And this is quite important because if you look at the literature, you will see there are many claims, discussion of actually having 2-qubit operations crossing fault tolerance. But what we've done here is plotted, at least from the papers that have published this information, this is the surface code threshold. This is the average error rate, which indeed crosses the threshold, but your maximal error rate or total error rate does not. Right? So in fact, one must be a little bit careful quoting these numbers. So what else could you do with this aside from simply benchmarking things? Is it a practical technique? You can also improve the depth of the circuit you can run for the simple fact that I showed you that when you multiply these error matrices together, if you have only diagonal components, they add up much more friendly than having those off-diagonal components. So in this case, we wanted to run a simulation, quantum simulation for nuclear collisions. So we write some effective field theory for a spin-independent and spin-dependent Hamiltonian for the scattering of two nuclear particles. So that's the field theory shown here in these Feynman diagrams. You can then trotterize that and break that up into a variational algorithm, which has pieces shown here. So you can see even the small piece of that variational algorithm is complicated. There's like 12 gate operations happening here, which start to become difficult to run on a noisy superconducting processor. But I want to show you here in this last slide that if I take the 4 scattering operators that I should get for 2 nucleons colliding, then these are the 4 states that you would predict, shown as these colored dots here. The lines are the result of an exact theory, which we can do for a small system. And you can see the quantum operation was terrible, right? Depending on, running these 20, 30 C0 gates in the sequence, it was terrible. But as I started to actually randomize the circuit and purify things, I end up with the plot on the lower right. And you can see for the same physical system, just tailoring the noise, the ability to do a quantum simulation is significantly improved in its quality. And if we want to talk about the role of noise mitigation or error mitigation versus error correction, et cetera, that's a longer discussion. I'm happy to have that in the break. But let me, seeing the time at 26 minutes, let me go ahead and take us to our summary slide. So here are the key takeaways. Coherent errors are quite common for us and typically in the field, and often dominate the error budget. So randomized benchmarking twirls different type of errors into a single channel. So this is the advantage of this method. You go ahead and put all your information in one channel to give you the average error rate. But note that this average error rate can be markedly different from the maximal error rate in your system because of bullet number 1, right? You have different types of errors. Adding random gates to quantum circuits tailors coherent noise into stochastic noise on average when I go ahead and measure many instances of this circuit. And such randomized compiling permits execution of deeper circuits, as I showed you in a moment. And perhaps also significant for benchmarking the quality of your hardware, going back to the title of the talk, using randomized benchmarking on randomly compiled circuits yields accurate benchmarks against fault-tolerant thresholds. And that's also what I've tried to illustrate here with the 2 pictures on the right. So with that, I thank you for your attention and bring the talk to a close, and I'm happy to take your questions.
Okay, thank you very much for this very interesting talk. If you have time, we have to move a little bit quick, but I'm pretty sure that there's questions from the audience.
Hi, Irfan. Thanks for the very interesting talk. So I was wondering about your statement, or basically about these permutations that you're operating. And as far as I understand, it's also kind of in the recent publications by companies or so, that's kind of one part of the error mitigation strategies. Do you have a good feeling how far this would bring us in terms of circuit depth or qubits? And what is the price to pay in that we have to apply all these permutations and then basically run longer experiments?
Yeah, that's a great question, and we've been doing this for a while, so we have a pretty good sense of where you can go with this and what the limitations are. So in a general sense, you think about quantum computation relying on your classical resources not being exponentially more complicated as you grow the circuit. The quantum complexity should grow, but not your classical overhead. So this kind of error mitigation requires polynomial more complexity. Okay, we can show that by mathematics for longer gate sequences. The result or improvement is also polynomial better. So in my mind, you will never be able to actually go ahead and run an error-corrected machine by this only, because the complexity is growing at the same rate as your benefit. The real advantage of quantum error correction is you have an exponential suppression after a threshold for a minimal number of parameters. So then the question is, how far can you go with this? It's a numerical question. Does it work still for 100 qubits, 1,000 qubits, million qubits, so on and so forth? So I think for hundreds of qubits, you will start to see certainly some improvement. And that's pretty good for an experimentalist, because that's probably the range I want to live in forever, right? After that, it becomes really a commercial endeavor. So for the near term, I can access regions of simulation and fidelity and physics that I couldn't. However, one must sort of take a deep breath and think about if this is sufficient to take you to some error-corrected regime. Unlikely, in my humble opinion. What is interesting, of course, is can this noise mitigation also help error correction? And that's something that's evolving at the moment. And that's also interesting, as if it may simply just be a way to improve your error correction routine. So I hope that answers your question.
Thanks a lot. Yeah.
Okay, I don't see any further questions, so let's thank Irfan again. Then our next speaker is Barbara Kraus. So she did her undergraduate and also